Welcome everyone. In this video I'm going to continue my CH32 tutorial series, and I'm going to continue the previous video's topic, but I will take another approach on it. So in the previous video I showed you how to work with the I2C, and we developed some standard libraries or standard functions which allow us to communicate with some devices. And then I showed you how to communicate with a magnetic encoder, the famous AS5600 magnetic encoder, and I also showed you how to read and write the pins of a I2C GPIO expander. So that was really straightforward because the functions were really easy, and I could use the built-in functionalities of the I2C, which are implemented in the CH32 environment. But now I have a slightly different hardware. I have a OLED display, and I'm going to implement my own library, which will allow us to print characters and numbers and text on the display. And since I have some future projects which would involve a very tiny 72 × 40 pixels OLED display, I will use this OLED display to implement the library, especially because I will use this in the future as well. I will rely on two external resources. Let's call them external resources. One is the SSD1306 display driver, and you can see that here this is actually applicable for the 128 × 64 dot matrix OLED display, but actually what is written in this datasheet is also applicable for our display. But the only difference is that instead of this resolution, we have a lower 72 × 40 pixels resolution. And when I show you the code and stuff like that, I will just copy-paste pictures from this datasheet. I will not jump back and forth between the datasheet and the developing environment, but I will just put an overlay picture on the video where it is applicable. And then we have this other datasheet, which is actually the specific datasheet of this display. So this is the 72 pixels by 40 pixels display datasheet. A very special advantage of this display datasheet is that it actually contains some sort of pseudocode. So I just quickly scroll there, and you can already see that the code actually here, and it's implementing everything. So it shows you how to implement the data transfer via I2C, and then how to create the start and stop conditions, and so on and so on. So I will also use this as the basis, and then I will implement my code based on this set of, let's say, instructions and codes, which I can find in both data sheets. So as usual, we are here in the developing environment. So let's create a new project. Let's select the applicable microcontroller family and the microcontroller. And let's create the project. So as usual, the main.c file already contains some code, so I remove the irrelevant parts. So here I remove this variable, and then as usual I remove these parts and this part. And then I start with my typical print, which prints the project name, so I can remember this in the future. And then as you can see it in the text as well, this will be a so-called bit-banged OLED display driver. And bit-banging basically means that we don't use the typical libraries which are already written, but we will bit by bit modify the I2C bus. So in this case, the SDA and SCL pins. And based on these modifications and configurations, we will be able to communicate with the external device, which is our OLED display. So to do that, we have to define the GPIO pins for this. And actually, I will choose the same pins that we have for the I2C communication by default, but I will define them as simple GPIO pins instead of using their alternative functions, which is the I2C function. So let's create the new function for initializing the I2C pins. And this will be a simple function without any parameters. So we have the structure here, and then we have to define the clock source as well. And that is on the APB2 bus. And we need the GPIO C and we need to enable the bus clock. So that's fine. And then we copy paste this guy here, put it here, and then we assign the different functions to the pin. So we have to select the pin, and as I said, we will still use the same pins that we have for the I2C, which means that this becomes a GPIO pin 1, and since this will be on the C port, this is PC1, and this is SDA. And then let's assign the mode, and this will be a little bit special, but not super difficult. So this will be a output with OD, which means open drain, and this is needed for the SDA pin. And then we have the speed, and that is just the default speed that we typically use. So that is the 30 megahertz. And then we initialize this part. And then I copy paste this bunch of code here. And then now we define pin 2 here, which is PC2, and that is the SCL pin. And SCL pin is only toggled, so set to low or high by the microcontroller. So this can be the push-pull configuration for the pin mode. So this doesn't have to be the open drain pin. And then in the datasheet I showed you that there is a function already provided with some pseudocode or with some very cryptic coding that actually takes care of the data transfer between the transmitter and the receiver. And that is basically the big bang I2C function. So let's implement it for the CH32 microcontroller. So first of all, you can see that this function takes a parameter, which is the data, and that is the data which will be shifted to the receiver, which is our display in this demonstration. And then I define or declare a variable which will be called counter, and it will start from 8. And then I create a while which will actually count down from the initial value of the counter, which is 8. So actually this will do the bit shifting, and it goes from 8 down to 0, or basically 7 to 0. So what we can do here is the following. So we create an if block here and an else block here, just to make our life easier. So here the condition should be the following. So we take the data, which is our 8-bit variable, and then we use the logical AND operation and we combine it with 0x80. And if it helps, then the 0x80 is nothing else than on binary is this number. So actually what happens here is a masking operation. So each time when the while loop arrives to this line, then it masks out the first bit in the data byte, and then checks if that becomes 1 or 0. If the bit becomes 1, then we enter the if part, and there we have to toggle the SDA pin accordingly. So what we do here is that we write a bit to the GPIO ports pin 1, and we put it into the set condition, and that means that the SDA is 1. Otherwise, if the masking returns 0, then we end up here. So actually we have to set the SDA to 0. And then we have to apply a little delay. 3 microseconds is enough. And then we have to toggle the clock pin. So here, instead of selecting the pin 1, I select the pin 2 and I set it. So that means that the SCL becomes 1. And since we have to toggle it and not just set it, we have to change its state to the opposite state. So after another following delay, the SCL pin has to be set to 0, which will result in this line. And then we wait again, and we shift our data to the left by 1 bit, which will look something like this. So what this means is that when the line is here, then the first bit of the data becomes the previously second bit. And I just put an illustration on the display so you see how the bit shifting works, but I explained it in so many of my videos, especially in this series, that you could know this by now. But basically every time we shift the data back, so actually we can go through all the 8 bits of the data variable, and then each time a new bit is masked out because of the shifting. So when the code comes back here, as the iteration goes more and more forward, then each time a different bit is masked and then checked if it's 0 or 1. So this is fine so far. And then we have to create another function which is starting the communication between the two I2C devices. So that will look something like this. And you can see that in the start function, the function should expect an 8-bit variable, which is the address. And this will be the I2C address of the device that we are communicating with. So for the starting, there is actually a timing chart in the datasheet. So you can see it, how it looks like. And when you implement it as a code, then that will look something like this. So I just take this line from here. And then you can see that the SDA has to be 0 first, and then we apply our usual 3 microseconds delay. And then here, the SCL has to be 1, and then we delay again. And now the SCL has to go low. We delay again, and we actually send the address. And then we have to do an acknowledgement, which is not implemented yet, but I write it here. But it will look something like this. And since we refer to this function here, actually the actual function has to be declared before the I2C start function. So first, the SDA pin has to be 1, and then the SCL pin has to follow it. So that means that this has to be set. And then the SCL pin, so pin 2, has to be 0. So something like this. So this is the acknowledgement condition. So I rename this here, and the stop function doesn't need any parameters, and it doesn't need any acknowledgement and any communication because we stopped the communication. And how it is stopped is that first the SCL is set to 1, so then this has to be set, and then the SDA has to go 0, and finally the SDA has to go high. So something like this. And there were 2 other functions implemented, and those functions were the command writing function and the data writing function. So let me implement them. So you can see that this function will also expect a parameter, and that is the command. So this is the parameter that we will send to the I2C device on the receiver side. So here we have to start the I2C, and here the address is expected here, as you can see. That will be an I2C address. And this is a parameter that we haven't implemented yet. So I just take this number here, go to the top of this wall code, and here where we have the global variables, I just declare this as an 8-bit variable. So that's that. So now we started the communication with this device. So what we need to do now is we need to send something to it. So we use this bitbang function, and we send the 0x00, so basically the 0 to the receiver, and this will essentially prepare it to receive a command. So then if the device on the receiving end, the display, receives this set of characters, basically a byte which equals to 0, then it will know that the next incoming byte will be the command. But before that, we have to acknowledge, and then we again use the bitbang function, and we send the actual command, which is passed to this function through this parameter. So this is done, and then another acknowledgement there, and then we stop the communication. And then we have to repeat this function, but for the data. So let me do that. So here we write data. So I rename this thing here as well. So the address is the same, but then here the data writing command is 0x40. And again, we have to acknowledge this, and then we have to send the data in this, which is received from this parameter of the function. And then another acknowledgement, and then we stop the communication. And that's all. So now we have all the functions ready. So we have to look at the SSD 1306 datasheet again, and there is a very nice software initialization chart there. Now I put it on the display as well. So actually we have to follow this, and you can see that each block contains a description, a very short description, plus some hexadecimal values. And those are the values that we have to send to the display as a command, and then the display will know that we try to configure certain parameters. And in addition to this chart, inside the datasheet there is a huge table which explains all these parameters, and then not only these commands, but what kind of parameters we can send with the commands. Because sometimes we just enable or disable a certain component on the display. For example, we turn on the display or turn off the display. So then the command only consists of one byte. But there are like double byte or 2 byte commands where you first send the command byte. Let's say you want to set the contrast, and then you send the actual contrast value to the display. So this is all described in the datasheet. I'm not going to go through it because you can read it by yourself and understand it better than I explain. But I just follow this chart, and then I implement a function. And that function is nothing else than just an initialize OLED function. So it looks like this. It doesn't need any parameters, nothing. And then we just go based on the function here. So we will have this. I just copy this, so I can always paste it if I need it. And then you can see that first we have to set the multiplexer. But before that, I like to apply this code which just sets the display off. And now we can take care of the multiplexer. And that you can see that that is 0xA8, and it expects another value. This is what I told you, that you need to see that table as well, and you can see what kind of values we can pass to this command. And I set this to this value. So this is fine so far. Then the next parameter is the offset, which is located on the D3 register address. And I don't apply any offset, so actually this becomes 0. Then the display start line is 0x40, and I don't need to do anything else here. Then we have to set the segment remap, and that is 0x and then A1. I apply the A1 parameter instead of the A0. Then the next one is the scan direction, and I choose C8 here, so 0x C8. And then the COM pin hardware configuration, in my case, it will be D8. So I just apply that, so 0x DA. And here 0x12 is my configuration, which means that I want to enable this functionality. And then, as I said again, we have a contrast, so that is 0x81, and then it needs a value which is the next byte, and I set it to 0x80. So that should be 128, so it's the middle value, because it can range from 0 to 255. Then we have this disable entire display on. So that is 0x and A4. Then the next is set normal display, and that is that the characters that we print, they are the lit pixels, and the characters that we don't print, they are not lit, or they are dim. Otherwise you can set it to inverse, but that would be the A7 command, and then everything will be bright except the characters that you print. So that's, yeah, obviously that's the inverse. So then we have 0x-A6 here. And then now we have to set the oscillator frequency. So let's do that. And that should be set by the D5, so 0x-D5. And then we have to set the values. And I use the default values, and that can be passed to this register using the 0x80 command or hexadecimal value. And then we need to enable the charge pump. This is also a 2-byte command, so 0x8D. And then how we enable it is that we write the 0x14 here. So this should work. And you can see that the last command here is the display on, but I actually have another command that I want to apply here because it's essential to make the display brighter than it is by default. So we have to select the proper let's say current reference or voltage reference on the board. So for that we write this register and set the 0x30 value on this. And finally we can turn the display on. So you can see that we have this function. So this must be initialized. But before that we actually have this function which is used for the pins. So we need to also initialize the pins. So I quickly compile. It looks fine. So then I can actually try to upload this to my microcontroller. And I can see that nothing happens, and that is kind of normal because I haven't set anything on the display. So we just configured the display. So either it is empty or full of garbage or full of the previous memory's content, depending on how we configured it. So now we actually have to print something on it. But before printing, we can erase everything from the display. So I think that's easier to learn and study how to erase the contents of the display. So erasing the display is technically writing zeros in each segment of the display. So the display, as you can see, it is built up by pages. In this specific display, we have 5 pages, so 0 to 4, and then we have 72 segments because that is the horizontal resolution of our display. And then, since we have 40 pixels vertically and we have 5 pages, that means that we have 8 pixels or 8 bits per segment. So that means that one page consists of 72 pixels along the x-axis and 8 pixels along the y-axis. And then we can address the page and we can address its sub-segments. And based on this, we can basically draw a bitmap, because we can set each segment's value to 1 or 0, and based on the display configuration, this will turn on or turn off the pixel. So we need a for loop which will iterate over the pages. So an 8-bit variable is enough here, and page 0, we start from that, and we go up to page 4, so page ++. So this is so far fine. So this will be our for loop which will go through each pages. And then in each page we have to send the set page address command. So I2C write command and then 0x22. Again, see it in the datasheet. And I just copy this. Now we need to switch to the actual page. So the default page address is B0, And then in each for loop iteration, we want to shift this with the number. So then in each iteration, we switch to the next page. And that's how we do it in an easy way. And then I select the right border of the display. And this is based on the display's resolution. So I set it to 0x4. And then we have to set the lower 4 bits and the higher 4 bits of the column address. So that will look something like this. So the lower bit is 0x0C and the higher bit is 0x11. So now we actually can switch between each pages with this, but we cannot do anything yet. So we nest a for loop into this already existing for loop. So this will now iterate through the segments. So we can do like this. So we start at segment 0 and then we go up all the way to 72 because we have 72 pixels along the horizontal axis or x-axis, and then segment plus plus. And then what we need to do here is we use the other I2C function, which is write data. And since my display is now already empty, I will fill up everything with pixel 1. So this will be, so I just compiled it. And now let me turn on the camera so you can see the display. There's the display. And now I press send. And now you can see that all our pixels are 1. So this is the display filled in. Very nice. And now I just, for fun, put this aside just a little bit. So now I change this line back to 0. And this is how we erase the display. There you go. Even you could see that there was a small delay in the display's resetting, let's say like that. So you could see how the pages were shifted and how the segments were erased like in a successive manner. So in order to be able to print anything on the display, like whatever resembles a character, we need to first study the ASCII table. And the ASCII table is nothing else than just you have a byte, and the value of the byte will tell you which character you have. For example, if your ASCII value is 0x21, then you receive the exclamation mark as the character. I can bring up a table, for example, like this, and we can see that the first column here on the left side, those are like non-relevant characters because those are some kind of command characters. But on the right hand side, the second column starting here, we have like intelligible characters. So this is the space, white space. And then the next one is the exclamation mark. And this is what I mentioned. So the 0x21 value on ASCII is the exclamation mark. And for example, 0x4b is the capital K, or the 0x75 is the small u, and so on and so on. So then we also know that the display is divided into pages. Each page is 8 pixels tall. So we can select that our characters will be 8 pixels tall. And then we can say that, let's say, okay, 5 segments is the width of our characters, regardless of what character we have. And then we can build a, let's call it vector or an array for each character, which consists of 5 bytes. So each byte is the 8 pixels within a segment, and then we have 5 of these because one character is built up by 5 segments. So let me bring up a drawing software and let me show you how we can draw actual characters. So I copied this segment illustration from the datasheet because this will come very handy when I try to show you how the segments work and how the characters work. So for example, we have the capital K character or letter, and that consists of 5 bytes. And that looks like something like this. So the first byte is 0x7F. The second one is 08. The third one is 14, and then 22, and then 41. And we have to check the bit representation of these hexadecimal values. So this is this, and then the next character is this, and then like this. So how this works is that we start from here, and then we read the numbers this direction, and then we go from LSB to MSB and see the value of each individual pixels. So that means that, for example, when we look at the first byte, then every pixel is set to 1 except the last one. So that will look something like this. And then afterwards, you can see that the first 3 pixels here, so these guys, they are 0, but the fourth one is 1. So that looks like this. And here, the third one is 1, the fourth is empty, and then the fifth is 1 again. And then in this line, you can see that we have the second one, and then the sixth one set to 1. And finally, the first one, and the n-1 is set to some value. And you can see that this is the letter K. And to be sure that we are doing something right, let's select 2 other characters. So let's make this capital M, and that is 0x7f, 0x02, 0x0c, 0x02, and 0x7f. You can see that along this line it's symmetrical because the letter M is symmetrical. And then another, let's say, more difficult letter, let's make this the G, capital G, and that is 0x3e. And actually how we can know these binary values is that either you Google them, or you take your calculator, change to programmer mode, and then you select hex mode, and you just simply type in the values. So this is 7f. So you see the binary number. So you do this diligent work, type in every character, and then you write down here. So I will just show the final result. So I wrote down everything with my ugly handwriting, and then we can do the same exercise. So we already know the 7f from the previous character. So we see that everything is 1 except the last one. And then here, the second one is 1, and then the 0c is the third and the fourth, and then it's mirrored, so then it looks like this, and then like this. So this also resembles the character M. And how the G looks like is that the first segment here, the first bit of the segment is 0, and then we have 5, 2, 3, 4, 5 ones. So this is like the backbone of the, or the spine of the G. And then here and here we have another pixels. So now I did this line. And then here what we can see is this is 1, 2 zeros, another 1, and then we have another 1 here. And then here, actually this is repeated like this. And then this is like the down part, so this part of the G. And then another skip, and then 1, 2, 3, 4. So this is the capital G. And as you can see, this also resembles a capital G. So you can see now how we can build up all the bitmaps. And obviously I did not do this, but what I did, you can see here, is that I just simply took a table from the internet. And then this is how it's done. So we saw that one character consists of 5 bytes. And let's go to the character G, for example, that we recently done. So these are the 5 bytes, and each byte corresponds to one column that I colored in according to the bits. So Then what we have to do here is that this has to be filled in the very same order as we have it in the ASCII table. So you can see that the 0th item in the array or matrix is the 20th or 0x20 item of the ASCII table. And later on we have to remember this number, but yeah, we have this. And then each subsequent value here follows it in the ASCII value. So you can see that these are the characters here in the comment, and then the character is followed by its ASCII value. And we will use this to build characters and build text. So let's not waste more time. Let me show you how to print a character. So we need a function, and this function will actually accept 3 arguments. So the first parameter is the page, because that will determine which line we print in. And then similarly to this, we have to have a column, or we can call this actually segment, it doesn't matter. And then the actual letter. So, or this could be character as well. It's up to you how you name it. As usual, we need the I2C write, and we need to write a command, and we need to set the page address. So this we already know from the erase character. We basically make the same function but with a bit extension. So then this won't be different much more. So this is the starting, plus we have the page. So if we want to print dynamically, this will allow us to do it. And then we have this right border as the end of the screen, and that is described by the 0x4 command. And now comes the fun part. So let me declare a variable which will be called address, and that is the default lower and higher address bits combined together. So I take this higher bit 0x11 and shift it up by 4, and then I combine this shifted up value with the original lower bit value, which will look like this. And what I do here is that I increment the address with the value of the segment, like this. So this will shift our printed characters along the x-axis. And then, now this increment is done, we have to decompose this new address into a new lower address and a new higher address. So what I do here is just I take this and I call this new lower address, and that is the address and a masking bit. So we just keep the lower part of the address. And then I do the same or similar with the higher address. So new higher, and that is then first I need to shift the address down by 4 bits, and then I mask it out again. And then now we obtain the new lower and higher addresses, and we can send them. So we have 2 commands here. One is the new lower here, and then the other has to be actually combined with this guy here, and have to be like this. So this is so far fine. So we have to write a for loop here, and it will look something like this. So what we have here is that we iterate through the 5 bytes inside the character. And then what we have to do is we have to push these characters to the display. And that is done by getting the font, extracting the letter that we passed as a variable here or parameter, and then in each iteration we shift out 1 byte from it. So then how it will look like is the following. So this is, for example, a letter here. And then this parameter is set in a way that the letter is actually the number inside that big array that I showed you. And that is actually the ASCII value minus 0x20, because everything is offset by 0x20. I will show you when we print the text. And then when that parameter is passed, then first this part looks up the whole line. And then when the for loop, this guy here, iterates, then we take the ith item of this vector or array. So in the 0th iteration, we pass this parameter to the display. In the first, or number 1, when I equals number 1, this is passed to the display, this is I equals 2, and so on and so on. So at the end, we will fill in those 5 segments on the display, or 5 columns. So this is how it will look like. And then this is done. So I will just take this, Ctrl C, and put it here. So the page, what we print on will be page 0 and segment 0. So this is the top left corner of the display. And for the letter, I pick number 1, because that is the, let's say, second item, because the first item is the 0, item 0, which is the space. So with this, we should see a exclamation mark in the top left corner of the display. So I compile this, it's fine. So I switch to the camera and I show you the camera right there. So I press upload. Ta-da! So we have an exclamation mark there. And just to show you, like briefly, if we didn't do anything else, then you can see that we called this is the number 1 item from this huge matrix. And the first item, or number 1 item, is this, because this is the number 0 item. So with this, yeah, I have no idea about the numbers, but I can just pass a ridiculously large number here, let's say 29, and then I just upload this. So we will see what characters we get here. So this is the equal sign, and that is, where is it? So this is 29. So 30, 31, 32, 33. So if I send 33, that should be the capital A. So let's see. Easy. So yeah, now you see how it works. So now we can print individual characters. So let me show you how to print the text. The text somehow has to end up on the display, right? So let's make this fancy. And what I mean by that is the following. We can go up all the way to this part where we have our USART described. And then what we can do is, I just put this here. We can introduce an interrupt. So we have USART1, and we will read. So we need the RxNE, and we enable this. So now we enable the interrupt on the USART, but we need this nested vector interrupt thingy as well. So what I'm going to do here is I format the code a bit, and then I need this, like this. And this we learned in a lesson, so I will just fill this in. But we have the channel, and this will be USART1 IRQN. So this will make sure that the interrupt is attached to the USART1 channel. And then we just have some priority here. We set it to 1. And then we have another sub priority, which is 0. And then we have to enable this channel, which is this one. And then this is done. So now I need a function that is taking care of the interrupts. So that has to be defined after the main here. So then we remember that that looks something like this. So you have to remember that this line has to be declared, otherwise the interrupt will not show up. and it will not work. And then we can actually define our interrupt. We look for the flag, which we know very well. So that is the USART get IT status, and then USART1, and then the IT is that interrupt that we defined in the configuration. And then we look for the status when it is not reset. So not equal reset. And then what happens inside this is that we put the received character into a variable. So I can actually have a local variable for this because we will not use it anywhere else. So received character, and that is USART received data, and then we receive the data from USART1. So this is nice. And then we have to check what's up with this character. So if the received character is a line break, then we actually have to finish our buffer. So now this buffer will be actually a global buffer, but I will first write it down here. So then this with the buffer index has to be a null terminate character. So when we receive the line end from the terminal, then in our local buffer on the microcontroller, we have to write not a line break, but a null terminate, because that for the buffer will indicate that this is the end. This is the final character. And then the buffer index will be reset to 0. And I will also have a flag, which I set to 1. And now I copy paste these to the top and define them properly. So what I did here is that I have a volatile character buffer array, and we need a size for it, and I just declare some ridiculously large buffer. I don't care about it, but actually if I would care, so actually we can calculate the maximum number of characters printed on the display, because the width of the characters are fixed. Every character is just 5 pixels wide, and we always print a dummy pixel after the character that we print. So actually one character is 6 characters wide, and our display is 72 pixels wide. And well, that's very lucky, because 72 can be divided by 6, which is 12. So each line can accommodate 12 characters, and we have 5 lines. So 5 times 12, that is 60. So actually we could print 60 characters, and since it's a USART buffer, we need to have an extra character for the null terminate. So if we are really nitpicking and we are low on memory, then this could be 61 characters, because we store 60 bytes, which is the 60 characters, plus 1 byte in the buffer, which will be the null terminate character. So that's how we could work with this. But I just have a ridiculously large sized stuff here. Let's go back to the interrupt. That's what we have here. So now this looks fine, but we have to continue this, because now we have to create the else, which will do the real stuff. So then we make sure that we are inside the buffer index. So if the buffer index is smaller than, let's say, 200 minus 1, then we save the current character inside the buffer. So buffer index, we increment, and we pass the received character to it. So it will look like this. So once again, we get the interrupt. So when we got the interrupt, then we pass the received character from the USART1, or received data, to the received character. We receive 1 byte at a time, so this is fine. If the byte which we received is a line break, then we put the null terminate character inside the buffer, and we don't need to increment the buffer index. And then we actually set the buffer index to 0, so the next writing can start from the beginning of the buffer. And then we indicate to the code that the USART is completed. So now we can handle the text that we got from the USART. Otherwise, if the character is not a line break or end line character, then we just keep filling up the buffer. So I press F7 just to see if I have any warnings. Okay, no warnings. So we can continue developing the code. This is now closed. So we can check if the USART completed is 1. That means that we have data to proceed with. We can reset this. And then just for fun, I can printf something. I can erase the display, and then I can print text, which will be the received buffer, and then 0, 0. So these will be the positions. And after this, I actually have to delete this. So 0 and 200, because we need to erase the buffer in order to keep it empty. Otherwise, if we don't erase, let's say now I print 60 characters, just as an example, and I don't erase the buffer, but in the next iteration, I just print 45 characters. So then that difference between 45 and 60, so those 15 other characters will be still in the buffer, and they will be printed with my text. So I have to erase it. And what actually the memset does is very simple and very funny, that it takes the received buffer, and then it fills up, let's say, 200 items in the buffer, starting from 0, with these characters. So actually I just set every character in my buffer to 0, and that is fine, because that is basically equivalent to erasing my display. But now we don't have this function. So let's implement the print text function. So similarly to the print character, the print text will also have 3 parameters. So we will point at the received buffer. We have to know where we start, so which page we start at, and which column or segment we start at. So then we create an internal variable which can be column, and that is the column start. So I just pass the received character or parameter to a local parameter here, because I will have for loops and I will have bit shifting. So I don't want to mess around with this value here. So this looks safer. And then we need a for loop. So what this for loop does is that it starts from 0, and then it actually goes through the received buffer and checks every item, and it goes until it catches this guy, the null terminate, because that indicates that our buffer is finished. So for example, we have this buffer with 200 items in it, but we only want to print 20 items. We don't need to iterate over the whole buffer again. We just iterate until we find the null terminate character. So that's how we do it. And then what we have here is that we need a character, which is the ith item of the received buffer. So that's fairly simple. If we want, we can print this on the terminal just to receive it and see if the parsing, let's say, works well. And then just to be sure, we check if this character is valid. If you remember, there was a few characters in the beginning of the ASCII table, which I said that they are not printable or not usable. That is every character before the space. And if we receive something like that, we would print some garbage on the display. So instead of doing that, like printing garbage on the display, I just neglect these parts. So what I need here is an if. And if the current character is less than this, which is the space character's ASCII value, or it is more than this, which I forgot what was this, then we print that, let's say, invalid character was received. And then we continue. So actually we skip the whole iteration of the for loop and go to the next character. Otherwise, we can continue with the for loop. And what we want to do here is that we create another local variable, which we call font position. And that will be if you remember, I told you that we will need to apply some kind of shifting in our big matrix, which holds all the fonts, where you have the 5 bytes for each font, because while the numbering inside the matrix starts from 0, so the first item in the matrix is the item number 0, that is not the 0th item in the ASCII table, but the first character inside our font, let's say, matrix, is this character, but that is the 0 character, but the ASCII value is this one, which I highlighted. This is the ASCII value of the space. So when I send the ASCII value of a number, I have to subtract this value from it, which I highlighted here. So then we will know the position of the ASCII number or ASCII character inside our table. So that's why we need to do this subtraction here. So then I print this just as a test. So I just say that, and then we just print this decimal number here, like this. And then we print the character, basically. And then we have the page start, which is nicely suggested here. And then we have the column. And then instead of the letter, we have the font position here. And now comes the smart part in the code. So now we actually have to increment the column by 6. And what we do is that we place the cursor on the display to the next character's beginning part. So because first we were in the 0 position, so segment number 0, and now we move to the segment number 6. And then we have to check actually if this column number is, if it became larger than this minus 6. And why I do it like this is I want to illustrate you how this works. So as I said, on the x-axis we have 72 characters, and then afterwards, if we would write further characters, they would run out of the, let's say, surface area of the screen. So after we incremented the column, then here we check if we are basically one character width below the capacity of the display along the x-axis. So that's what happens here. And if this happens, then if we are outside the capacity because the column is larger than this value, which is 66, then I reset my starting position to 0, basically, and I increment the page start by 1. So we move to the next line. So the next character, which would otherwise run out of the surface of the display, will be printed in the next line. So this is fine. And then we check another thing. If you remember, our page capacity is 5 pages. So page 0 to page 4. So if we would print into something larger than page number 4, then we have to exit because there are no more pages. So then this is done. So I just press the compile just to see if I messed up something. No. And if you remember, we already have the print text here. So let me upload this to the display. Let me open the serial terminal, and then we need this guy here. You need to see the display. So let's just try a simple stuff here. And it works. So actually I can show you that you can see the ASCII characters which we printed here. And if I get rid of this camera for a moment, I just want to show you something that we can see each character's ASCII value here. Maybe it's not the luckiest combination, but if I go back to the ASCII table that I showed you earlier, then actually we can see that, for example, we printed the character 72, and that is here, the big capital H. And then we printed the 101, which is the E character here. And then we have twice the 108, so that is L. So So now you can see how this works. But then what the font position is that essentially subtracting the 0x20 or 32 decimal from the current character. So then we get the problem, because you can see it on the left side. I put a red frame there, that those are invalid characters. And then the first valid character is this space character. And that is where we start with our huge matrix as well, which is this guy here. So therefore, we always have to subtract 0x20 or decimal 32 to have intelligible characters and get the proper characters. So let's do it. Let's enter a bit more text. So now you can see how it works. We have those characters 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So at the end we have a space, and you can see that after the space, that equation that I showed you previously, if I find it, this here behind the serial terminal, that kicked in, and then I put the character A in the next line, because then otherwise that would have been outside this column larger than 72 minus 6. So that's that. And you can see that also the terminal writes here that invalid character was received, and that is the enter. That's the line break. So if I press the line break now, you can see that I essentially erased the display with that, because I sent an empty character, and then that buffer was empty, and that was printed on the display. So then the display is empty. But here, I can do this. So now you can see that the display is not empty. So I printed something on it. And I can print a lot of numbers. I can print even more numbers. And it shows up very nicely. And actually, you can see that, so 1, 2, 3, 4, 5, 6, 7, 8, 9. 10, 11, 12. So this should fit one line. And you can see that this fits one line. So, and then we have now 12 characters, and we have 5 lines total. So that's 60 characters. So we can actually fit 60 characters on this display. And of course, this is tiny, of course, a very small display, but for certain purposes, this is nice. And also, now since we know how to create a character, how the segments and pages work, we can actually make larger fonts. I will not do that, that will be your homework, but you can see that it's possible. And with this, I'm thankful for your attention. I even typed it in. So I end my video here, because I think I explained most of the parts that I wanted to share. So first and foremost, visit my website, because I have all the resources there. I uploaded a lot of information regarding the source code, regarding the bit shifting, regarding all these things, how the ASCII characters are handled. So other than the resources which I show in the video, there are more resources and links on my website. Also, I put all the product links there, the display, the microcontroller, the breadboard, whatever I use in the video. So please check my website and check if one of those links can help you to purchase one of these items. Also, if you like this kind of content, please consider becoming the member of my channel. So for example, it would allow me to buy these kind of gadgets and make more tutorials based on them. So I hope that this video was useful to you. I hope you learned something, and see you in the next video.